Hello, this is Paul from First Attack. In this video, let's prove Theorem 1.6.3, which tells us the conditions for invertibility. One of the conditions for invertibility. See, let's say if A is a square matrix, if B is also a square matrix satisfying B times A equals I identity, then B is the inverse. Okay, or it just switch the order of A, B, and A times B is equal to I. And the same, we also get B is the inverse of A. And this is super important because the theorem just simplify our definition of the inverse matrix. Let me just say it's important because it simplifies the definition of the invertibility. See, it's like this. If A times B equals B times A equals identity, remember this, then B is the inverse of A. That's the definition. And you can look at the definition. We have two conditions exactly. We have to verify A times B equals I, and also verify B times A equals I. But here, see, and the first, we only need to verify part or half of the condition, or another half of the condition. Then we will get the same result. Let's see why this is true. Look at the first. And if we know A, if A is true and then B, it's easy to get it. We just use A. Okay. So if B times A equals I, how to say? First, we need to just look at if A is invertible. See, imagine. So we simply say if A is invertible, and then we easily get this, and then see B times A equals I. Therefore, so I easily get this. This equals I, right? So I can do multiplication. I times the inverse of A to the right, and I also times the inverse of A, because A is invertible, right? And then the inverse of A exists and the unique. If I times this, and we can cancel this part because that is I. So what do we get? We get B equals inverse of A. Okay. So therefore, this is too easy. So now we need to say why A is invertible. Okay. So why A is invertible. This is the major one. And the equivalence theorem. Okay. Remember that equivalence theorem. The equivalence theorem gives us 1.5.3. Says if A is invertible, it's just equivalent to A times X equals a zero matrix has only trivial solution. Only trivial solution, which means the solution is only zero solution. Look at it, which means X should be zero. Okay, is this true? So now we just look at this part. Is this true? Yeah, it's easy. Okay, because I know B times A equals I. If I say if X is a solution of this linear system, I can left multiply the matrix B. Okay, see, I can left multiply B to here and then left multiply B here, and the B times A is I. Disappear is identity, so X is zero. So that's true, right? Or let me just put it down a little. That's true because if A times X equals 0, see, I can multiply B to here. I multiply B to here. Okay, so I put this. What does this mean? This means B times A. By the condition, it says B times A equals I, right? Okay, so this is a I matrix. Okay, B times 0, of course, is 0. Therefore, okay, and then we can get X equals 0 vector, which means that's true. If this is true and A is invertible, definitely is true, right? Okay, good. If A is invertible by the calculation, we know B is the inverse of A. Yeah, that's for A. Therefore, yeah, this is true. If BA equals I, B is the inverse. And then we look at the second B. If A times B equals I, and do you think B is the inverse of A? We just use the result from A. A means what? The first, okay, is the inverse of the second. We just use. If let's see, if A B equals I, if A B equals I, and then by the first proof for A, we know the first should be the inverse of the second. Therefore, the first A should be the inverse of the second, right? We already proved. And we need to say B is the inverse of A. Therefore, I can find B is the inverse of inverse. And the inverse of that's a property we learned of before. Okay, so the inverse of B is A. Therefore, this equal the inverse of A. So that's the proof. Thank you.